All right, it is now time to move on to section 3.2. We are going to here be dealing a lot with trig. So get comfortable because we do use a lot of trig in Calc 2. So before I start on here, I want to recap a few things from a trig class you might have had, whether it was actually trig or pre-calculus or that kind of stuff. This was taught in there. These are some identities we are going to use. So I just wanted to recap them and write them down, and you should too. Cosine squared plus sine squared is equal to 1. At the same time, 1 plus tangent squared is equal to secant squared. Also, sine squared is equal to 1/2 minus 1/2 cosine of 2x. Make sure there's a 2 in there. And cosine squared is equal to 1/2 plus 1/2 cosine of 2x. These are going to be really helpful for today's class, okay? So, as a recap, we actually did one almost exactly like this, if not exactly like this, in section 3.1. But example number 1, we're going to do integral of cosine cubed of x times sine of x. We did one pretty much exactly like this one in section 3.1. For this one, we are going to use something called U substitution. We have used it a lot here, right? You learned it at the very end of Cal 1. I'm going to pick a U so that it's just something cubed instead of having all of this stuff, right? Well, since cosine is what's being cubed, I'm going to let that be the U, which would mean du would have to be negative sine of x, which is great because I have the sine part. I need the minus sign, so put the minus sign out front and out front again. Would make this just negative integral. Cosine is the u, so u cubed du, which is easy. Add 1 to the power, negative u to the 4th over 4 plus c, and we said u was cosine. So it's not very hard whenever I have a product of cosine and of the sine, because if u is equal to cosine, my du is equal to the negative sign. So when there's a product of these two, I want to do this kind of thing. The problem is it's not always as clear. And let me show you what I mean with example number 2. Example number 2 is the integral of cosine squared x times sine cubed of x dx. So this one looks a lot how this one does, but the difference will be if I let u be equal to cosine here, the du will still be equal to sine. Why is that, or sorry, the negative sign. Why is that bad? Because I have sine cubed, not just a sine. So this doesn't work as it stands. So what I want to do instead is I want to use my knowledge of trig to rewrite this so that it works out how this one did. Okay. So remember we said, so in order to work out, I would need just a lone sine, right? So I want this to have just a sine of x, not sine raised to some stuff, just a sine. Since it's sine cubed, I could rewrite it as the integral of cosine squared of x. I can pull out 2 of them and make it sine squared of x, leaving the one that I want. So that's helpful, right? Because it left out a sign that I want. That's great. Because that's what I want for the du, right? But it still wouldn't work just yet because, again, if I let u be equal to cosine, du would be negative sine, which would take care of the cosines and then would take care of this sine, but my sine squared would still be here. But thankfully, I have a rule for sine squared. That's where I bring in my trig stuff. Cosine squared plus sine squared is equal to 1, which means sine squared is equal to 1 minus cosine squared. So for this sine squared, instead of having sine squared, I could rewrite it, integral cosine squared of x, I could rewrite it as 1 minus cosine squared times sine x dx, which solves our problem because now I can let u be equal to cosine. So du is negative sine, which would give me negative integral cosine squared, so that's u squared. 1 minus cosine squared would be 1 minus u squared. Sine x dx is the du. And I can do that one because I can distribute my u squared. U squared times 1 is just u squared. U squared times u squared is u to the fourth. You can use the power rule. Add 1 would give me u to the third divided by my new power, which is 3. Add 1 would make it u to the fifth divided by my new power, which is 5, which would give me negative. My u is cosine. Negative would make it plus cosine to the fifth plus c. So what the general rule here is if there's a power that is odd, I want to bring one of them out, leaving me here with a sine squared. If this had been sine to the fifth, it would have left me with sine to the fourth here, which meant I would have then had to square this out because to have sine to the fourth means sine squared squared. So then this would have been squared, and then I would have had to square it again. Does that make sense? To break it down to where I just have sine squared, which I could then use my trig rules and move on like that instead. Had this have been sine squared cosine to the third, it would have worked the same exact way, except I would have pulled cosine out here and had cosine squared, and then made this 1 minus sine squared. So it would have worked the same exact way. They would have just flip-flopped. Let's do another example. Integral of sine squared x dx. This one does not have a cosine, meaning that the u substitution stuff would not work. However, remember we do have a rule for sine squared, saying sine squared is equal to 1/2 minus 1/2 cosine of 2x. So I can rewrite it like that. And then break it up into two separate ones. So this would be integral 1/2 dx minus 1/2 integral cosine of 2x dx. This one isn't hard because it's just a constant, right? So that would just give me 1/2 x. Easy enough. For this one, I can use u substitution with u equal to 2x, which would make du 2 dx. I need a 2 there. In order to put a 2 out there, I need to divide by 2, which would make this 1/4. So minus 1/4 integral cosine of u du. The antiderivative of cosine is sine. So this is going to be 1/2 x minus 1/4 sine of u, and I said u was 2x plus c. So that one here just kind of used trig stuff to break it down. Let's do another example, example number 4. Integral cosine to the 8th, sine to the 5th. So this one again, I want to use u substitution because I have cosine times a sine. However, I don't just have a sine, I have sine to the 5th. So pull one of them out. Cosine to the 8th x. Pulling out one would give me sine to the 4th left over. Sine to the fourth is like saying sine squared squared. So this becomes integral cosine to the eighth sine squared. I forgot the x. Sine squared is 1 minus cosine squared. But since it's to the fourth, it's sine squared squared. So take that and square it times sine x dx. So now, since I just have just one sign, I can go ahead and do u substitution. U equals cosine, so du is negative sine. So this is going to give me negative integral cosine to the eighth becomes u to the eighth. 1 minus cosine squared becomes u squared squared. Sine x dx becomes du. First, let's square out 1 minus u squared. 1 minus u squared is u to the fourth minus 2u squared plus 1. Now distribute u to the eighth. That becomes u to the 12th minus 2u to the sixth plus u to the eighth, not to the sixth. 8 plus 2 is 10. What am I thinking? Du. Then I can use my power rule, which would just give me negative u to the 13th over 13. Negative makes it plus 2u to the 11th over 11 minus u to the 9th over 9th plus c. And we said u was cosine. So negative cosine to the 13th x over 13 plus 2 cosine to the 11th x over 11 minus cosine to the 9th x over 9 plus c. So again, the idea is I want u to be cosine, so I need to pull out a sine, which still left me with the sine term, which means I need to then change this sine to a cosine, which is when I use my trig rules that I have here. Next, let's do example number 5. This one's kind of a doozy simply because you've got to do something more than once, but it still isn't hard. It's using the same ideas as in example number 3, but you just got to do it twice. So for example number 5, that's integral of sine to the fourth dx. So just like in example number 3, this doesn't have a cosine, so I can't use u substitution. So instead, I've got to use my rule that sine squared is equal to 1/2 minus 1/2 cosine of 2x. But this is squared, right, because it's to the fourth. So it's sine squared squared. So this is actually going to be the integral 1/2 minus 1/2 cosine 2x. That whole quantity squared. So now let's square it out. Remember, squaring means I write it twice, right? If you do that and work it out, you end up with 1/4 cosine squared 2x minus 1/2, because it would be 1/2 times 1/2 is 1/4 times 2 is 1/2. Cosine of 2x plus 1/4. And then now we can break this down piece by piece. 1/4 integral of cosine squared 2x minus 1/2 integral cosine of 2x plus integral of 1/4. All of these should have a dx. I forgot them though. So for this first one, I have cosine squared, which again means I've got to use my trig rule that I have here. Cosine squared is equal to 1/2 plus 1/2 cosine of 2x. But it already has 2x, which means that becomes 4x. So 1/4 integral of 1/2 plus 1/2 cosine of 4x dx. For this one, I can use u substitution with u equals 2x, which means du is going to be 2, which means I need another 1/2 out here, which will make this minus 1/2 sine of 2x. Antiderivative of 1/4 is just 1/4 x. Now let's do this one. 1/4 times 1/2 is 1/8. The antiderivative of 1/8 is 1/8 x. For this one, 1/4 times 1/2 is 1/8. I would then use u is equal to 4x, which means I would need to divide by 4, which gives me 1/32 sine of 4x. And then all this stuff doesn't change. And lastly, 1/8 x plus 1/4 x. The common denominator would be an 8. So this is 2/8 x. 1 plus 2 is 3. So 3/8x. There are no other like terms because this is 4x, this is 2x. So no other like terms. So the rest of them can just stay. So I use a lot of different trig rules there and antiderivative rules and everything. But if any of it doesn't make sense, tell me. It's okay. It will not make me mad, I promise. Just let me know. There are some other helpful trig rules you would have learned in trig or pre-cal. If you have sine of ax times sine of bx, you can rewrite that as 1/2 cosine of a minus bx minus 1/2 cosine of a plus bx. If you have sine of ax times cosine of bx, that's 1/2 sine of a minus bx plus 1/2 sine of a plus bx. And then if I have cosine of ax times cosine of bx, that's 1/2 cosine of a minus bx plus 1/2 cosine of a plus bx. So I can use those to solve ones that kind of look like this here. Okay. So example number 6, integral of sine of 5x times cosine of 3x. Integral sine of 5x cosine of 3x dx. This has sine times cosine, which means I'm going to use this rule right here. 1/2 sine of a minus b, so that's going to be integral of 1/2 sine a minus b would be 5 minus 3, so 2x, plus 1/2 sine a plus bx. 5 plus 3 is 8 dx. So this one isn't too hard because I would use u substitution here. U would be equal to 2x, which would mean du would be equal to 2. So I've got to divide it by 2, which would give me 1/4. The antiderivative of sine is negative cosine. 2x. Same thing over here. U would be 8x, which would mean du would be equal to 8, which would mean I need to divide it by 8, which would give me 1/16. The antiderivative of sine is negative cosine. So negative 1/16 cosine of 8x plus c. So again, we just need to rewrite them into nicer ways. Example number 7 is the same kind of thing. Integral of, where'd it go? There it is. Cosine of 6x times cosine of 5x dx. Same thing. Cosine times cosine is going to be this rule right here. 1/2 cosine a minus bx plus 1/2 cosine a plus bx. So this is going to be integral 1/2 cosine a minus bx. 6 minus 5 is 1. So 1x plus 1/2 cosine a plus bx. 6 plus 5 is 11. So do the same kind of thing here. The antiderivative of cosine is just a sine, so that's just 1/2 sine x, easy enough. Here I would need u is equal to 11x, which would mean du is equal to 11. Divide by that and you get 1/22. Antiderivative is again sine plus c. Easy enough. So now moving beyond sine and cosine, I can do the same kind of thing with secant and tangent. Okay. So first things first, I want to review some derivative and antiderivative rules from Cal 1. All of these are from Cal 1, but have a chance right here to write them down or whatever you need to do. Hit pause, that kind of thing. And I'm going to try the same thing with secant and tangent. So, example number 8. Integral of secant to the 5th times tangent. So again, since I have secant times tangent in there, I want u substitution, okay? So I want to find where there is a derivative in there somewhere. So looking at these rules right here, the derivative of tangent is secant squared. So if I let u be equal to tangent, then secant squared is good, but I would still have secant to the 3rd. So that doesn't quite work here. Whereas the derivative of secant is secant tangent. So this would work. So I can pull one secant out to like join that guy right here, which would give me integral of secant to the 4th times secant x tangent x, because then I can let u be equal to secant x, and the du would be secant tangent, which I have. That would take care of all my terms, right? Because secant to the 4th would then just become u to the 4th. Secant tangent dx would all become the du. So that works, so I want to run with that. Antiderivative of u to the 4th is u to the 5th over 5 plus c, and my u was secant x. So secant to the 5th x over 5 plus c. So that one worked out really nicely. I just borrowed a secant from here to be included with the du. So it worked out. Let's see if example number 9 works out nicely as well. Integral of tangent to the 6th times secant to the 4th. So this one, if I let u be equal to secant, I would need du to be secant tangent. So I could borrow a secant here and a tangent here, but I would be still left with tangent to the 5th. So that wouldn't work there. So let's try letting u be equal to tangent and see what happens there. If u is tangent, the derivative of that is secant squared. So I would take secant squared here, but I would still be left with a secant squared. But that's okay, because from our trig rules, we know secant squared is equal to 1 plus tangent squared. So that's fine. So just like before, tangent to the 6x, I want just a secant squared so that I can use that for the du. If I take out secant squared, I'm left with secant squared. So I can use this for the du part, which means I need this to be a tangent. But like we said, secant squared is equal to 1 plus tangent squared. So make that 1 plus tangent squared. And now I'm good. Because now tangent is the u, so this is u to the 6th times 1 plus u squared. Secant squared dx is the du. So that's good. Distribute u to the 6th, u to the 6th plus u to the 8th. Antiderivative, u to the 7th over 7 plus u to the 9th over 9th plus c. And then plug in what we said the u was. And we're all set. So once again, just like with the start of class, the idea is I want to write it using the trig rules, right? So I'm going to use my trig rules to make sure it works out really nicely. Let's move on to example number 10. Integral tangent to the 5th x secant cubed x dx. So let's see what happens here. If I let u be equal to tangent, du would have to be secant squared, which would mean I would be left with secant to the 1st, which is not good because I need secant squared in order to use my rule here. So this would not work. Again, because secant squared would go away, and I would be left with secant to the 1st, which that doesn't help me. So u being tangent doesn't work. So let's try u being equal to secant. So du would be secant tangent. So I would borrow a secant, leaving me with secant squared, so that's good. I would be left with tangent to the 4th, which is fine, because I know something about tangent squared, so I can just square that. So I'm good there. So borrow a tangent, leaving me with tangent to the 4th. Borrow a secant, leaving me with secant squared, times secant times tangent. And since u is equal to secant, I want secant to stay there, meaning I want to rewrite tangent. Tangent squared, if I move this one over here, tangent squared is secant squared minus 1. But since it's to the 4th, I'm squaring that again. So squared times secant squared x times secant x times tangent x dx. Now I'm good because this is du, and I can use these for the u terms. So this becomes integral u squared minus 1 squared times u squared du. And now just work this out. U squared minus 1 squared is u to the 4th minus 2u squared plus 1 times u squared. Distribute the u squared. U to the 6th minus 2u to the 4th plus u squared. Take the antiderivative like we've done 1,000 times. This becomes u to the 7th over 7 minus 2u to the 5th over 5 plus u to the 3rd over 3 plus c. And u was secant. So secant to the 7th x over 7 minus 2 secant to the 5th over 5 plus secant to the 3rd over 3 plus c. And there we have it. Once again, if any of that does not make sense, tell me. I would rather you tell me than just having a hard time with it. For those following along with the handout, we're going to actually omit 11 and 12 because I'm going to cover those right here an easier way. So we're just not even going to worry about doing this the hard way. Omit 11 and 12. We're going to go right on to these reduction formulas. Integral of secant to the nx is equal to 1 over that n minus 1 secant to the power of n minus 2x times tangent of x plus n minus 2 over n minus 1. Integral of secant to the n minus 2x dx. And tangent to the n of x is equal to 1 over n minus 1 tangent n minus 1x minus integral of tangent n minus 2x dx. Whew, that's a lot. So let's use those to do examples 13 and 14. Example number 13 wants us to do the integral of secant to the third x dx. By the reduction formula, with n being equal to 3, I can rewrite it to be this instead. So that's going to be equal to 1 over 3 minus 1. 3 minus 1 is 2. So 1/2 secant to the power of 3 minus 2, which is just a 1, so I can just leave it off, x tangent of x, plus n minus 2. 3 minus 2 is 1 over 3 minus 1, which is 2. Integral secant to the power of 3 minus 2 is just secant x dx. So the only part I have left is just this part right here. And luckily we know that from Cal 1, integral of secant x is equal to the natural log of the absolute value of secant x plus tangent x plus c. So this becomes 1/2 secant x tangent x plus 1/2 natural log absolute value secant x plus tangent x plus c. So that makes it way easier than doing it the long way, which we would have done on examples 11 and 12. Lastly, example number 14 does one of those with tangent. Integral of tangent to the fourth x dx. Use the reduction formula here. 1 over 4 minus 1 gives me 1/3 tangent to the 4 minus 1, so tangent cubed. 1 over 3 tangent cubed of x minus the integral. Tangent to the power of 4 minus 2. 4 minus 2 is 2. It's the integral of tangent squared x dx. I don't have a rule over here for tangent squared, which means I've got to do it again. I've got to do this rule one more time using the reduction formula. So this is going to be, the first part's not going to change. Minus. Use it for tangent squared, so it would be 1 over 2 minus 1 tangent to the 2 minus 1. So 1 over 1 tangent to the 1, so that just becomes tangent. Minus the integral, tangent to the 2 minus 2. 2 minus 2 is 0, tangent to the 0 is just 1. So this is going to become 1/3 tangent cubed x minus tangent of x plus antiderivative of 1 is just x plus c. So as I always say, and as I will say a billion more times, if anything doesn't make sense, please let me know.